Section 1.4, composition of functions. Function composition is the operation where we plug one function into another. If we let f of x and g of x be functions, then function composition is going to be denoted with this little circle, which will be referred to as f composed with g at x, and this represents f of g of x, where g of x is the input into the function of f of x. To illustrate how function composition works, let's take a look at the example of f composed with g of 0. By definition, f composed with g of 0 would equal f of g of 0. The way we evaluate the composition at a specific value is we start with the innermost function and work our way out. The best way to think of function composition is through a system of machines. We start off with some sort of value, in this case 0. 0 goes through this machine, which we label g, and g is going to transform 0 according to its function rule. And we obtain g of 0. Now, looking at the table, we can see that when x equals 0, g equals 4. So g of 0 equals 4, meaning if we plug 0 into g, it will output 4. So f of g of 0 will equal 4. Now, 4 is sent into the machine labeled f. F is going to follow its rules, and it's going to output f of 4. Going to the table, we can see f of 4 equals 18. So f composed with g at 0 will equal 18. Now let's take a look at g composed with f of 0. Notice how we're switching the order of g and f this time. So g composed with f at 0 will equal g of f of 0. Now, first we'll evaluate the f of 0. Going to our table, we can see that f of 0 is negative 1. So g of f of 0 is equal to g of negative 1. Now to evaluate g of negative 1, going to our table, we can see that when x equals negative 1, g is 5. So g of negative 1 equals 5. So g composed with f of 0 equals 5. Notice that when we switch the order of the functions in the composition, we are obtaining different answers. Function composition is not commutative, like addition or multiplication. So the order in which we are composing the functions does matter. Next, we're going to evaluate f composed with f of 2, which means here we are composing f with itself. F composed with f of 2 equals f of 2. Using our table, we can see when x equals 2, f equals 3. Now we need to evaluate f of 3. Going back to our table, we can see that when x equals 3, f equals 8. So f of 3 equals 8. So f composed with f at 2 will equal 8. Next, we'll evaluate g composed with g of 3. By definition, this will equal g of 3. Going to our table, when x equals 3, g will equal 1, so g of 3 will be equal to g of 1. Now to evaluate g of 1, from the table we see when x equals 1, g equals 3. So g composed with g of 3 will equal 3. Now we're going to evaluate composition of functions using graphs. First, we're going to find f of g of 2. First, we need to evaluate g of 2. Looking at the graph for g, we can see that the point 2, 0 is on the graph of g, so g of 2 equals 0. Now we need to evaluate f of 0. Using the graph of f, we can see the point 0, 4 is on the graph, which means f of 0 equals 4. So f of g of 2 will equal 4. Next, we'll evaluate h of f of 2. We'll start by evaluating f of 2. Going to the graph of f, we see the point 2, 5. That tells us f of 2 will equal 5. So now we have to evaluate h of 5. Going to the graph of h, we see h has the point 5, 5, so h of 5 will equal 5. So h of f of 2 equals 5. Next, we're going to evaluate f of h of g of 1. Here, we're composing 3 functions together, but whether it's 2 or 3 functions, the strategy remains the same, that we're going to evaluate starting from the inside and work our way out. So using the graph of g to evaluate g of 1, we see the point 1, 3, so g of 1 will equal 3. Now we can use the graph of h to evaluate h of 3. In our graph of h, we see the point 3, 3, so h of 3 will equal 3. Next, we need to evaluate f of 3. Going to our graph of f, f has the point 3, 2. That tells us f of 3 will equal 2. So f of h of g of 1 will equal 2. Now we're going to find the composition of functions defined by equations. We're going to start by composing f with g. From the definition, this equals f of g of x. G of x is x squared plus 2, so f of g of x equals f of x plus 2. Now we're inputting the expression x plus 2 in our function f, which means anywhere that I see an x in our f of x, that is going to be replaced with the expression x plus 2. So f of x plus 2 is going to equal 3 times x. X will become the x squared plus 2, then minus 1. Notice how I'm keeping parentheses around the x plus 2. Anytime you're replacing a variable with an expression, you should always keep that expression in parentheses in case you have to distribute because of multiplication. Now we can finish simplifying, distribute into 3, and then combine our like terms, which is the 6 minus 1, and we get that f of g of x equals 3x squared plus 5. Next, we'll find g composed with f of x, which is equal to g of f of x. F of x is 3x minus 1, so we'll replace f of x with the 3x minus 1. Now to evaluate g of 3x minus 1, everywhere we see an x in g of x, we're going to replace it with 3x minus 1. So x squared becomes 3x minus 1 squared. Remember to keep those parentheses around the 3x minus 1, and then plus 2. Now when we multiply out the 3x minus 1 squared, we're going to use the special multiplication rule. A plus b squared equals a squared plus 2ab plus b squared. So applying that formula, we get that 3x minus 1 squared is 9x squared minus 6x plus 1. Combined our like terms, and we get 9x squared minus 6x plus 3. Next, we're going to evaluate f composed with g of 3, and we're going to look at 2 approaches of how to do this. The first approach is to use the definition. That is f composed with g of 3 equals f of g of 3. To find g of 3, we would plug 3 into our function g of x. G of x is x squared plus 2, so g of 3 will be 3 squared plus 2, which is 11. Now to evaluate f of 11, we would take 11, plug it into our function f. So f of 11 equals 3 times 11 minus 1, which equals 32. The second approach we can take capitalizes on the fact that earlier we found that f composed with g of x equals 3x squared plus 5. So we already have a formula for f composed with g. So our second approach would be to just plug 3 into that formula, which would be 3 times 3 squared plus 5, which also equals 32. The first approach is perfectly fine if you're just evaluating a composition at a single value, but if we have to evaluate a composition at several different values, it is very helpful to find the formula first, as we would in part 1, and then you can plug those different values into the formula. However, there is one detail we do have to be careful of in order for the formula to work properly, and that is something we're going to discuss in a few slides. Next, let f of x equal 1 over x minus 1 and g of x equals 1 over x minus 2. We're going to start off, first we're going to find f composed with g of x, and we're going to write it in the simplest form we can. From the definition, this is equal to f of g of x. G of x, we're told, is 1 over x minus 2, so we'll replace g of x with 1 over x minus 2, and we have f of 1 over x minus 2, which means anywhere we see x in f of x, we're going to replace it with 1 over x minus 2. And when we do, we get 1 all over 1 over x minus 2 minus 1. Now, I do have parentheses around the 1 over x minus 2, which is what we replaced x with, but since there's no distributing, we can drop the parentheses. Now we have a complex fraction, which are not that nice to look at. We're going to clear the denominators by multiplying the numerator and the denominator by x minus 2. The reason why we're going to do this is when we do the multiplication, the numerator is going to stay x minus 2 since we're multiplying by 1. But in our denominator, when we distribute, we have x minus 2 over x minus 2 minus x minus 2. The x minus 2's will cancel in the denominator, leaving us with 1. And we get x minus 2 all over 1 minus the quantity x minus 2. And you can see that we got rid of the complex fraction. We can still do a little cleaning up in the denominator, distribute in negative 1, and combine like terms. And we get that f of g of x equals to x minus 2 over 3 minus x. Now let's evaluate f of g of 2 by using the definition of composition of functions. So f of g of 2, to evaluate, first we're going to plug 2 into our function g. Since g of x is 1 over x minus 2, then g of 2 is 1 over 2 minus 2, but 2 minus 2 is 0. And the one number we can't divide by is 0. So by definition, f of g of 2 is undefined because 2 makes g of x undefined. Now let's evaluate f of g of 2, but this time we're going to use the formula we found earlier. If we were to use the formula we found earlier, we have 2 minus 2 over 3 minus 2, which is 0 over 1, which is 0. So the question becomes, which of these are correct? One method, I'm getting that my function at 2 is undefined, while the other one, I'm getting 0. Since in the second bullet point, we found that f of g of 2 is undefined through the definition, then that is the correct answer. Despite our work with the shortcut, 0 could not be correct, because the definition trumps any shortcut we could take. This illustrates why we have to be very careful with function composition when it comes to using a formula as a shortcut to evaluate our function at different values. We have to pay very close attention to what we're allowed to plug into the function, because when we manipulate that function, it may not be obvious as to what we can and cannot plug in. In order to figure out when it's appropriate to use the formula of the composition to evaluate our composition at specific values, we need to understand how to find the domain of the composition. In other words, what are we actually allowed to plug into the composition? So we're going to suppose that f and g are both functions. In order for a value f to be in the domain of the composition of f and g, we need to meet certain criteria. If we think about the machine metaphor that we were using at the very beginning, if we start off with x, in order for the composition to work, x has to be something that can be passed through g. If x cannot be passed through g, then the composition breaks, the machine won't work, and our composition will be undefined. So the first criteria is that x has to be in the domain of g of x. Now, if x is in the domain of g of x, then we can pass x through g, and g spits out g of x. Now, to finish the composition, we have to pass g of x through function f. In order for the composition to work, g of x has to be a value we can plug into f. In other words, g of x has to be in the domain of f of x. If g of x is not in the domain of f of x, the composition is undefined, but if g of x is in the domain of f of x, then we obtain f of g of x. So if we take a look at the two functions we composed in the last example, f of x equals 1 over x minus 1, g of x equals 1 over x minus 2. First, we need to figure out what values of x are in the domain of g of x. Well, g of x is 1 over x minus 2. The one number we're not allowed to divide by is 0. So g of x is defined as long as x minus 2 is not 0. So g of x will be defined as long as x is not 2. So that's the first condition. Our first condition is that x cannot be 2. But now let's go to condition 2. If we take a look at our function f is defined as long as x minus 1 is not 0, because that's the only number we can't divide by. And if we solve for x, we get that x cannot be 1. So in order for g of x to be in the domain of f of x, then g of x cannot be 1. Or in other words, 1 over x minus 2 cannot be 1. To solve for x, we'll solve this just like an equation, multiply both sides by x minus 2, and we get that 1 cannot equal x minus 2, or in other words, x cannot be 3. So what we've just gotten from this work is if x is any number other than 2, x will pass through g. However, in order to make sure our g of x can pass through f, x cannot be 3 as well, because 3 will pass through g. However, g of 3 is equal to 1, and 1 is not allowed to go through f. So the only two values that make my composition undefined are 2 and 3. So my domain in interval notation will be negative infinity to 2, representing all the numbers smaller than 2, 2 to 3, representing all the numbers between 2 and 3, and 3 to infinity, representing all the numbers bigger than 3. So from this domain, if I were to use the formula that we found in the previous example as a shortcut, by knowing the domain first, I know the two values I'm not allowed to plug in are 2 and 3. 3, we could immediately tell from our equation that we couldn't plug in because our denominator was 3 minus x, 3 minus 3 is 0, that'd be undefined. But if we relied solely on the simplified equation of f composite g, we would miss that we're not allowed to plug in 2. So when finding the domain of the composition of functions, it's very important that we pay attention to how the composition is created. Next, we're going to find the domain of f composite g of x, where f of x is the fourth root of x, and g of x is 3x plus 2. Again, I'm not going to figure out what the composition is as a formula. I'm going to focus on g of x and f of x and the two conditions highlighted above. If we look at g of x equals 3x plus 2. 3x plus 2 does not contain division, does not contain any even roots, does not contain any logarithms. So our domain of g of x would be negative infinity to infinity. So if we think about our first condition, x has to be in the domain of g of x, then any choice of x will be in the domain of g of x, since g of x has a domain of all real numbers. Now we'll turn our attention to condition 2. Condition 2, g of x has to be in the domain of f of x. If we take a look at f of x here, f of x has a fourth root. The only numbers we're not allowed to take the fourth root of are negative numbers. So the only way our fourth root of x can be defined is if x is greater than or equal to 0. So taking a look at condition 2, we want g of x to be in the domain of f of x, which means we need g of x to be greater than or equal to 0. G of x is 3x plus 2. And when we solve our inequality, we get that x is greater than or equal to 2/3. So from our work, what is the domain of our composition? Well, anything can pass through g of x. But in order for g of x to pass through our function f, x would have to be greater than or equal to negative 2/3. So if x is anything less than negative 2/3, it can pass through g, but g of x won't pass through f. Numbers smaller than negative 2/3 cannot be in our domain. So that only leaves us with the numbers that are negative 2/3 or larger. Or in other words, negative 2/3 to infinity with a square bracket around the negative 2/3. Next, we're going to talk about function decomposition. Function decomposition is the process of undoing function composition. Suppose we're working with a function of h of x. Function decomposition is the process of finding two simpler functions, f and g, such that h of x equals f of x composed with g of x. There are many different ways to decompose a function, but one thing to keep in mind is f of x and g of x should not be the original function we're decomposing. This skill is very important in calculus, where you're dealing with very complicated problems, and being able to decompose those complicated functions into simpler functions allows us to perform calculus operations a lot easier. The way we're going to decompose our function is first we're going to identify g of x. G of x is going to be the expression that's trapped within some sort of operation. If we take a look at the 1 over x minus 5, notice how x minus 5 is trapped in the denominator of the division. So we're going to make g of x minus 5. Now, how do we obtain f of x? F of x is obtained by replacing the expression we call g of x with x inside of our function that we're trying to decompose. So if we replace the x minus 5 with x, we get that f of x would equal 1 over x. If we want to check that our decomposition is correct, we can find f of g of x, which is f of x minus 5, which is 1 over x minus 5, which is our original function. Neither f nor g is our original function h, so that is one way we can decompose our function. Now let's take a look at h of x equals the square root of x squared plus 1. Again, g of x is going to be the expression trapped within inside of an operation. Here, the x squared plus 1 is being square rooted, so we're going to make g of x squared plus 1. To find f of x, we're going to replace the x squared plus 1 with x, and that'll leave us with the square root of x. So f of x is the square root of x, while g of x is x squared plus 1. As I stated before, there are many ways to decompose a function. Another option we could take is we can make g of x squared. Now, if we replace x squared with x, f of x becomes the square root of x plus 1. Now, both of these are decompositions of h of x. However, we typically prefer our decompositions where f of x is as simple as possible, which if we take a look at f of x equals the square root of x, that is much simpler than f of x equals the square root of x plus 1. And by simpler, I mean less operations we have to do to evaluate the function. So it's often more preferred that we perform the first type of decomposition. And the first style of decomposition, where we make our f of x as simple as possible, is often referred to as the natural decomposition. I'm not saying that the second decomposition is wrong, it's just not as preferred as the first. If we take a look at h of x, which equals the absolute value of 2x squared plus x minus 1, we can see our expression trapped inside of those absolute values is the 2x squared plus x minus 1. So that is what will make our g of x. As for our f of x, we'll replace the 2x squared plus x minus 1 with x, and that leaves us with f of x equals the absolute value of x. Again, there is another way we can decompose h of x. I'll leave that as an exercise for you all to try, but this is the more preferred decomposition because the f of x is as simple as we can make it. Next, we're going to talk about an expression that is the foundation to one of the major operations in calculus, and that is the difference quotient. The difference quotient represents the average rate of change of a function f of x from x1 equals a to x2 equals a plus h. The formula for the difference quotient is f of a plus h minus f of a all over h, where h is not equal to 0. Our goal in these problems is to try to simplify the difference quotient as much as possible. We consider the difference quotient fully simplified if the h in the denominator is canceled out. We're going to take a look at a strategy that will help us evaluate the difference quotient, and we're going to apply it to the function f of x equals 5x plus 2. The first step is we're going to evaluate f of a plus h. To evaluate f of a plus h, that means we're taking a plus h and plugging it in for x. So in the 5x plus 2, the x becomes a plus h. And then from there, we can proceed to simplify by distributing it 5. And there's no like terms to collect here, so f of a plus h is as simple as we can make it. Now we'll move on to step 2, which is to simplify f of a plus h minus f of a. We already found what f of a plus h was in the previous step. Now we're going to subtract f of a, which is our function f of x, where we replace x with a, which would be 5a plus 2. Now we can go ahead and simplify. First, distribute in the negative 1. Then we can combine our like terms, and through combining like terms, we can see the 5a's and the 2's will cancel. We're left with 5h. Now we can move on to step 3. Step 3, we can finish simplifying our difference quotient. Through steps 1 and 2, we know what the numerator of our difference quotient is. We found that our numerator was 5h. Now we can proceed to simplify farther, and we can see h is a common factor in the numerator and denominator, so they will cancel. And we get that our difference quotient of 5x plus 2 is 5, which does make sense. 5x plus 2 is a linear function. One of the main properties of linear functions is their average rate of change is constant, and the slope represents the average rate of change. Since the slope of our function is 5, it makes sense that our difference quotient in this example was also 5. Now we're going to find the difference quotient of f of x equals 3x squared plus 2x minus 1. Going through our process, step 1, find f of a plus h, which means everywhere we see x, we're going to replace with a plus h, and then we're going to expand and simplify as much as we can. First, we'll expand the a plus h squared using our special formula. We have a squared plus 2ah plus h squared. Then we'll distribute. First, distribute the 3 into the a squared plus 2ah plus h squared. Distribute the 2 into the a plus h, and there's our f of a plus h. Unfortunately, there's no like terms to collect, so that's as simple as we can make the f of a plus h. Now we can move to step 2. We'll take the f of a plus h that we found in the previous step, and we will subtract f of a. And remember, f of a is going to be f of x, where we replace x with a. We'll distribute the negative 1 into the parentheses, and take a look at combining like terms, and we can see the 3a's cancel, the 2a's cancel, 1's cancel. And we're left with 2ah plus 3h squared plus 2h. Now we can move on to step 3, where we evaluate our difference quotient. Thanks to steps 1 and 2, we know that the numerator of our difference quotient is 6ah plus 3h squared plus 2h, and we just have to divide that by h. In the numerator, notice how every term has an h as a common factor, so we'll factor out h, and our numerator becomes h times the quantity 6a plus 3h plus 2. The h's will cancel, and we get that our difference quotient of 3x squared plus 2x minus 1 is 6a plus 3h plus 2.